Good morning, class. We're still having that warmer weather, but it will get cooler. I think that I will look forward to that. But every time I say that, I'll get some kind of congestion. I think we're hoping that the masks we wear keep us, safe from the COVID. And I think maybe the mask I'm wearing has kept me safe from just the regular flu that runs around. But I still get the sniffles and some things, but haven't gotten anything really, really bad. So I, as you continue to do your work and all that, be safe. When you get out, make sure you're following the protocols with the mask to keep yourself safe, and keep the people around you safe too. So what I wanted to do today is if I have some time, I may go and do also maybe another work problem just to maybe get to an example that I didn't cover last class, even though I've covered quite a bit. And today I just want to take some examples from your book and also some examples from some old tests just to kind of recap everything. And like I say, recap is good. And I know a lot of you are working, all of you are working hard. And so I'm sure you have plenty of good skills. I do want to say this. If you look on the practice test, you'll see some problems where you're asked to like substantiate something, like do a proof or give justification. On the test that you take, the online test, you will not have problems where you've got to do a formal proof. You will have, though, when you look at the practice test, the computations where you have to use the ideas of the proof. And if you understand how things fit together, then that's going to help you with the problem. So there won't be a problem where it says prove that this is the derivative of the inverse sine or something like that. That's great for a face-to-face class, but it's not as appropriate for the online class. So the computations will be very similar. And like I say before, I'll send out another message. You'll do all of your work on separate sheets of paper. As you go through the Blackboard test, you'll select an answer, move on to the next problem, put all of your work down on sheets of paper. When you're done with the test on Blackboard, scan everything into one file, and there'll be a tab for test one work for you to submit your work. And it has to be one file. I prefer a PDF, but whatever file that puts all of your papers in order, numeric order, so that I can scroll through them. And this again is a plus for you because again, as I grade your test, I'll look at the Blackboard test for a raw score. But say you miss a question, I look at your work and I'm like, okay, there's good work here. So that would mean partial credit. And there won't be that many problems. I'd say around maybe 12 problems similar to the practice test. So what I'm trying to do is make a very fair test. Well, I've made a very fair test. So if you've worked through the lectures, you've worked through your WebAssign, worked through your quizzes, and you have a foundational understanding, then you will be very prepared for this test. So again, the idea, and a lot of you have asked me this, what's the best way to study for math? The best way to study for math is just to do consistent work and do work every day. Even if you don't have more than maybe 30 minutes or an hour, you've got a real busy day, do a couple of problems, work through an example from lecture. That's always a good way to look at things. Okay, so let me share the screen and we'll do some examples. Now, what I want to do, you know how we started our class, we began with the inverse trig derivatives and things. And so I want to look at some of that. And also just remind you, think like you did in your pre-calculus class when you had the first introduction to the inverse trig functions. So our first example will be to write an algebraic expression. So I'll just say, let me adjust this. I always have to adjust this just a little bit. There we go. So write an algebraic expression and the variables always change, it doesn't matter, write an algebraic expression for the composition. So in this case, our variable is u, even though it could be x or whatever. We'll just stick to that like we're doing WebAssign. So we have cosine of the inverse tangent of u. So we want an algebraic expression. So often, a lot of times as we're doing work in calculus, especially when we get to trigonometric substitution, there'll be many instances where we have compositions and we're going to have to get back to the original variable. So we'll do more of this as we work through the next chapter. So again, this is good stuff. I mean, we're going to actually use this. So what we can do, as you did before, we can just make an assignment for the inner function, so to speak. So let u be, in this case, well, excuse me, let's not, well, I don't want to use u. Let's use theta, inverse tangent of u. And of course, we know that the inverse tangent lives between negative pi over 2 and pi over 2. And then, of course, we can write this and by taking tangent of both sides to create a more usable form in terms of a right triangle. So I'm putting in more steps here than we normally do, but that's good. So we have tangent of theta is actually u over 1 if we just write a ratio. So now what we can do is construct a quadrant 1 angle, a triangle, an acute triangle that describes the algebra, as long as we make sure we keep up with the sign of the expression. So we can put theta here. And of course, this is opposite over adjacent. And then, of course, by the Pythagorean theorem, we'll just get 1 plus u squared. So this describes the algebra of our particular substitution. And so now we need basically cosine of theta. So this equals cosine of theta. And cosine of theta, and again, what we want to do when we look at this is say, okay, the cosine function, you know, our algebraic expression has to exhibit the correct sign. The cosine function in the first and fourth quadrants is positive. So we expect our particular expression to also be positive, and we'll have that. So just as a side, cosine theta is positive. And so now we have, if you will, adjacent over hypotenuse, which has the correct sign. And also something that could vary in sign if we needed, if we had an expression with just a plain old u in it, that would offer a possibility to change sign if that were the case, if we needed that case. Now, of course, this is correct. And this is a nice rendering of the problem. You could certainly rationalize it if you wanted to by multiplying by root 1 plus u squared and dividing by root 1 plus u squared if you like. And so a lot of times when you're looking at responses, they may be rationalized, and so you can work it forward. The main thing is that when you do your work, you do your work completely, and then you're able to make a good selection. This, at least for the first time, will save you from having to input everything. You write everything down, and that may be a little less stressful. So I've thought about that as a fair way to test you without bringing up too much anxiety. So again, expect just composition problems where we're using the concepts of the inverse trig functions just as a means of kind of getting you set up for the calculus of the inverse trig functions. Okay, the next example we want to do is just a derivative. The directions will say find dy dx. And so in this case, we have y equals the inverse secant 4x plus 7. So the intention here is not to just push you into the deep end. It's just to test you on the foundational knowledge. So we've done some difficult problems. So if you can do those challenging problems, you're set. And that's what I try to do. I like the lecture to challenge you and at least give you something to think about. And then when you get to the test, you're like, wow, I put in some time and I know what I'm doing. So again, hopefully that'll help to relieve a little bit of stress. So in this case, we know from our Calculus 1 course that the dy dx is just the derivative here, the y prime. So we can compute that. So y prime will be the derivative of the inverse secant 4x plus 7. Now, just as a little aside here, we know what the derivative of the inverse secant is. We actually derived it. Remember, we'll have u is equal to 4x plus a 7. And so u prime, or du dx, will just be 4. So that will be something we'll use. So now we have what? And just as a reminder, let me just go ahead and write this up. The derivative, we'll do the chain rule version. So the derivative of the inverse secant we'll have u prime upstairs, and downstairs we have the absolute value of u times the square root of u squared minus 1. So that's what we derived in class. So we'll just fill this in. So now we have 1, and we have the absolute value of u, 4x plus 7. And then I'll use brackets. Then we have 4x plus 7, quantity squared, minus 1 to the 1/2 times 4. Now, when you look at this particular expression here, you're thinking, well, you could expand the radicand here, but it's certainly not required. And then when you look at responses, you just look for the one that is equivalent to this. So if we wanted to finish this, we could certainly leave this as it is in the factored form. So we have 4, absolute value 4x plus 7, square root 4x plus 7, quantity squared minus 1. So this would just be a problem to basically let me know that you understand how to utilize the formulas for the inverse trig functions. Not necessarily very difficult, but certainly very important. And of course, we know that this derivative formula impacts the formula for the antiderivative, where we have the working the formula backwards for the inverse secant integral form, again, which has an absolute value in the antiderivative. So this is an important formula. So let's look at another derivative. And so in this case, we want dy dx, so compute dy dx. And in this case, we have y equals inverse tangent 4x cubed. So we're getting the chain rule, so to speak, which is fine. So just to remind ourselves, we know that if we have the inverse tangent of u, I'll just use the prime notation. This will just be u prime divided by 1 plus u squared. Again, these formulas are probably very familiar to you now as you work through these. What maybe initially looked a little abstract is now commonplace, because these forms arise so often. They'll be commonplace to you. I wish every integral technique would become commonplace, but it's always a function of how much you use it as to how much you remember clearly. So now y prime will be the derivative the inverse tangent of 4x quantity cubed. So we can use the chain rule. So the outer function derivative is the power function. So we have 3 inverse tangent 4x to the second power. And then we multiply by the derivative of the inner function, which is the inverse tangent of 4x. So here you could just say u equals 4x. U prime is just 4. Just doing prime, not the differentials like we do with the integrals, but you know the difference. So now we'll have times. In this case, we'll apply the formula. So we'll have, go ahead and write this way. So we have 4 upstairs, and then we have 1 plus 4x quantity squared. So if you will, we can go ahead and push everything together and have the 12. So we can have 12 inverse tangent 4x quantity squared divided by 1 plus 16x squared. So when you look at problems like this, again, just testing the basic formulation. If they're fractions, of course, you did your web assign, you deal with the fractions. There was some practice with throwing some logarithms in and the hyperbolics. That again is just to make you aware of this. I'm not going to put real extreme problems on the test that were like, oh, I didn't even do hyperbolics in Cal 1 and Professor Ron expects us to know it. I want you to be aware of it. But just remember that if I put anything on the test, it will be the foundational problems. And also, if I've worked a problem, that's always a good problem to know. But it doesn't necessarily mean like, oh, well, that's the hardest problem we did. I bet that's going to be on the test. Not necessarily. I want you to know what I've covered, but I want you to have a good foundational understanding. Now, let's look at a couple of integrals. So for instance, we found the most difficult type of integral would actually require us to complete the square. And so you could expect to completing the square. But again, the integrals will be reasonable and they will require that you know the formulas for the inverse trig integrals. So let's just do an example here that covers that, where we really don't have to complete the square, but if you had to, I've shown you how to do it. So in this case, if you look at this particular example and you think about this, this one's similar to that long-winded problem we had that was a definite integral, but notice the square is completed. So when you look at this, you're thinking inverse sine and just break it up into 2 pieces. And then the other portion here, the inverse sine, this portion would be, we're thinking rig for a calculus 1 integral. So again, since the square is already completed, that does save us quite a bit of work. So what we can do is just go ahead and look at the radicand or the argument of the radical. And this is 49 minus, excuse me, let me not differentiate it yet, 9x squared. So du will be negative 18x dx. And so now we can think about rigging the calculus 1 integral. Again, everything's set up. So the first thing we want to do is just break it up. So we've got a 3 here. And we have our square root, 49 minus 9x squared. And then for the second part, we have minus 2x square root 49 minus 9x squared dx. And so now when we look at this, we think inverse sine. When we look at this, we think that we need the additional factor here of the 9 so we can run the negative in and adjust it. So for the second part, if you will, here now we can look at this and say for the inverse sine function, so I won't use the same letters here, unfortunately. I've already used the U, but I'll go ahead and write it in a more advantageous way. So we have, I'll use brackets here, 7 squared minus 3x quantity squared to the 1/2. And so now if you want to think of this as a W, W equals 3x, dW equals 3 dx. So that's set up. We've got the 3. And then, of course, the A is equal to 7. So the 3, and of course, I didn't stick in the dx there. Let me go ahead and add that. So the 3 dx that we have here makes this table ready. So we don't have any further adjustment to do here. Now for this one, we're going to go ahead and move the negative back in and then adjust with a 9. So we'll have in this particular case, 9 times the negative 2x dx to give us the negative 18 dx. And well, here, let me do this. Permit me to do this. Let me just go ahead and write this upstairs because that's how we're going to have to differentiate or integrate it. Go ahead and bring it upstairs, just like that. So we can add 1 divided by the new power. And then we can do, if you will, the 9 negative 2x dx. So the negative 2x was already there. And of course, we need the 9 here to render the differential negative 18x dx. And then, of course, we have to accommodate that 9 with a factor of 1/9. So this makes this table ready. Again, this is table ready. Fortunately, we had the 3 here. And now this is table ready with the additional factor of 1/9. Okay, so now we can apply the inverse sine form for the antiderivative. Remember, the 7, the 1/a does not occur in this formula. It's only in the argument. So we get the inverse sine of, in this case, 3x divided by 7. And now here, we've got our 1/9, so plus 1/9, add 1 divided by the new power. The new power is 1/2. Reciprocal of 1/2 is 2. So we have times 2, 49 minus 9x squared to the 1/2 plus a constant. And now when we look at this particular example, we can just clean this up a little bit and we're done. Again, very straightforward, but just the basic techniques we've been doing. 2/9 square root 49 minus 9x squared plus a constant. So this is a good example, not as tedious as when we have to complete the square and rig a little bit differently. But again, if you can do the problems we've already done in class, then these are very straightforward. And I want you to be able to do some definite integrals too. So let's look at one of those. So again, basic construct. We will continue to use this. Once we finish center of mass and move into the techniques of integration, we do this over and over. It'll become commonplace. And just like the long-winded problems in chapter 7, some of the integrals get long-winded just because we have lots of pieces. So let's do an example here. Let's see here. We've got the integral pi over 4 to pi over 2 And we have the integral 2 sine 2 theta. And then we have 1 plus cosine squared 2 theta. So at least the problem here is reasonable. We have the same argument throughout, so you don't have to use any double angle identity, which again, we will review when we get to the trigonometric integrals and all. We'll hash through all of those identities that you probably wanted to forget. So now when we look at this, we think, okay, we're set up for the inverse tangent integration form. And so if we want to think about this, let's just go ahead and rewrite this in a user-friendly way. So we have pi over 4, pi over 2, 2 sine 2 theta d theta. And then, of course, now we can write these as squares. 1 is 1 squared, obviously, and then plus cosine 2 theta quantity squared. So now, just as a little aside, remember the integral du. I didn't write this for the last one, but this one has the 1 over a squared plus u squared is just 1 over a inverse tangent u over a plus a constant. So just like we did for the inverse sine, but the inverse sine formula does not have the 1 over a. That absorbs in the derivation. So now we can look at this and say, okay, well, u is cosine 2 theta. All right, something in my little bit of dust. 2 theta du will now be the derivative of cosine is the negative sign, so we get negative sine 2 theta times the derivative of 2 theta, which is 2 d theta. So we have du is negative 2 sine 2 theta d theta. And then, of course, the a is just 1. So that's even easier. So now when we look at this problem, it's really table ready except for the negative. So all we have to do is adjust with the negative and pay for it. So this will give us pi over 4, pi over 2, and now we have negative 2 sine 2 theta d theta, and then we have 1 squared plus cosine 2 theta quantity squared, and then of course we pay for it for the negative outside. So now this is table ready. So again, the same song and dance, just like we do with all the applications of the integral. So now when we apply this formula, we have the negative 1 over 1 is just 1. And so we have inverse tangent of u over a. So that just leaves us with inverse tangent of cosine 2 theta. Evaluated pi over 4, pi over 2. So we have the negative, which we can factor. So we can substitute the pi over 2 here. Again, remember the 2's will absorb, and that just leaves us inverse tangent of cosine of pi. That we can see. We don't have to write that. We see with the pi's over 2, the 2's absorb. And then for the lower limit, we have inverse tangent. And now notice here, the 2 absorbs into the 4, giving us pi over 2. So we have cosine pi over 2. So again, what I'm doing here is cosine 2 times pi over 2, which gives us this. And here I'm doing cosine 2 times pi over 4, which gives us this. So again, it's always good to write out the steps. And if you do something in your head, then you can do a little explanation above so you have something to go back and check. Put in as much detail as you need. And I try to put plenty of detail. Unfortunately, detail means different things to different people. So put in as many steps that will make it clear to me that you understand. And so now we have negative. So now the cosine of pi is -1. So we have inverse tangent of -1. And now, of course, the cosine of pi over 2 is 0. So we have minus inverse tangent of 0. Now, of course, the inverse tangent function is odd, so the negative factors. So we have the negative of negative inverse tangent of 1. And then, of course, the inverse tangent of 0 is just 0. So now the two negatives absorb. So we have the negative of the negative. In this case, inverse tangent of 1 is pi over 4. So the negative of the negative is just the positive. So in this case, we get pi over 4. So this is a nice example that just, again, uses the basic construct and then, of course, your unit circle. And of course, those pages that I sent you from the end papers of your book, you can certainly use those as reference. Again, the unit circle is something you should know, but I don't want you to again stress about that. If you're in a face-to-face setting, I always make sure that students have access. If they have a question, I'll write something on the board. So you can certainly have that. I mean, you'll have your notes available as you test, and I'm certainly not opposed to that. The idea is that if I can recall in grad school, if I ever had or undergrad, if I ever had an open book test, it really made no difference because if you didn't know the material, you could stare at notes, it wouldn't help. But it's always nice to have a reference like, oh yes, this is the formula that I need. So that is no issue for me. Now, what I want to do is look at some applications. And then I do want to say something about an arc length example that you did on your WebAssign. In some cases, I'll just do a review from a WebAssign problem that I was asked several times. What I try to do is keep up with the types of problems that are or questions that you pose on WebAssign. And I'm like, oh, this is becoming a popular problem. So I may do a couple of those. So here we have a simple example. And we want to compute the area. So in this case, compute area of region bounded by the curves. And of course, it's sometimes written as curves, sometimes it's written as bounded by the equations, bounded by the functions. Basically, you make a sketch of the region to figure out the limits of integration like we always have. And in this case, we have y equals 3x plus 3, and we have y equals x squared plus 3. Okay, so when you look at this, you're thinking, all right, well, we've got a linear function and we've got a quadratic function, so this isn't so bad. So first, we're thinking, okay, we've got two functions, and so if we're going to have a region, they'll necessarily have to intersect. So we can go ahead and look at the intersection. So just equate the ordinates. So we have x squared plus 3 equals 3x plus 3. And of course, in this case, the 3's absorb. So we have x squared equals 3x if and only if x squared minus 3x equals 0. Then, of course, we can factor here. So we have x times x minus 3 equals 0. Now, of course, by zero product, we have x equals 0 or x equals 3. Now, just based on the concavity of the structure, we don't have to solve it. You notice in a lot of these problems, we don't really have to solve complicated inequalities because we know the concavity of this function will necessarily make it the lower curve. So one beautiful part of doing these problems is that we have enough knowledge of the curves that we don't really have to do that much work, even though it seems like we're doing a lot of work. So now we can think, all right, we've got this nice quadratic college algebra function. And notice here with the 0, we can just go ahead and use this. We have 0, comma 3. And then, of course, with the 3 here, this will give us a 3, and then, of course, a 9 plus a 3, or a 12. So we can spread these things out. So we got a 0, we have a 1, a 2, and a 3. And just to make it look pretty, we'll just say we go up to 12 here, and then mark the scale as you like. And then we have our nice quadratic function that's been raised by 3. So I'll just say here, let me kind of do this so it looks, so say 10. And so 3 we'll put about right here. Again, this is not Rembrandt, so don't try to make it look like Rembrandt, just nice and, reasonable. So here's our quadratic function. And then, of course, the linear function will connect these 2 points. And then, of course, we have this region. So just a standard problem that you're very accustomed to doing. So now we have y equals 3x plus 3. And then, of course, y equals x squared plus 3. So the geometry is good to us. So now we can just apply the definition for area bounded by curves. And notice here, we'll just say, okay, well, the independent variable that's going to work very nicely for us is clearly x in this case. So x will live between 0 and 3, as we have noted here. And so now, again, you can just take an x and think about what we do with all the applications, and just do the upper curve minus the lower curve. So again, this reminds us, with the other ones, we're interested in lengths, we're interested in, distance to the axis of revolution, as you well know, but the areas are probably the simplest thing to do. So we have area, by definition, will be the integral from 0 to 3. And then we have the upper curve minus the lower curve. So we have 3x, plus 3 minus the lower curve, which will be minus the quantity x squared plus 3. So the integral 0 to 3, we've got a nice lower limit of 0. We're always happy for that. So we have 3x plus 3, and then we have minus x squared, distributing the negative, minus 3 dx. So now, of course, the 3's absorb, and we're left with a 3x minus an x squared. So if you like, minus x squared plus 3x dx. Now, of course, when we're working on a problem, if there's ever any nice symmetry, at least based on the integral, we'll use it, but we don't have any here. So now we'll just add 1, divide by the new power. And so we have a 3, and then, of course, an x squared over 2. So add 1, divide by the new power. Add 1, divide by the new power. So this basically gives us what? Negative 1/3 x cubed plus 3 halves x squared. So now we can substitute by the fundamental theorem. Of course, look, the lower limit annihilates both of these terms. So we're, again, very happy for that. So we have negative 1/3 times 3 to the third plus 3 halves times 3 squared. And of course, the remaining terms will just give us 0. So you can just put in a 0 that these are annihilated. You wouldn't have to just write down a bunch of zeros. I clearly do that, or just leave it out altogether because that's clear. All right. So now notice one of the 3's absorbed here, and that'll give us a negative 3 squared. And then, of course, here we've got a bunch of 3's. So we have plus 3 cubed 3 times 3 squared divided by 2. So in this case, we could just factor the 3 squared. So 3 squared, we're left with a 3 halves minus a 1. So again, when we have the 3 squared here, that leaves behind the 3 halves. We factor the 3 squared here, that leaves behind the negative 1. So we have 9, and then just a common denominator of 2. So we have 3 minus 2. So this will be 9 times 1/2, or 9 halves. So this is the same song and dance. At least when you work through the test, we're not so spread out. The test will usually be fairly focused. Again, that changes with everybody, but you see that we end up doing this with pretty much all of the problems. We're kind of stuck with it. So the area problems kind of give us the framework for how we work with most of the problems in this class, at least for chapter 7. Okay. So now what I want to do is work through, let's see, on the test, if there is a parenthetical remark that says use a particular method, I would like you to do that. Like if I say use the shell method, I would like you to use the shell method. However, if you're calculating the volume of a solid of revolution and it does not specify, then you can use, you are at your leisure to use any method. So if I don't, if I ask you to do an arc length, obviously you'll have to use the arc length formula or area of a surface. I mean, you don't really have any choice there, but with the volumes, you certainly do. If there's no specification as to the technique, you feel free to use whatever approach that you feel is good. So let's look here at this particular example, and I want to do an example from the WebAssign too, and that's going to be, I think that's going to be the washer method. So I'll be sure to do that. So let's look at one of these, and then I'll do an arc length. In this case, it says compute the volume of the solid of revolution. And in this case, we revolve a region about a particular axis, and here we revolve about y-axis. So I'll say revolve region about, now you don't have to write all this down when you do your problems, you just write, you're reading the problem and you write down what you need. And in this case, the region, we have x equals 3y minus y squared. And then of course we have the y-axis. Now sometimes it'll be x equals 0, and sometimes the problem will be good to you and just say y-axis. So I mean, take whatever you can. So again, when we look at this, we think, all right, well, we'll just go ahead and write this out. X in this case equals negative y squared plus a 3y. So if you like, in this case, we can just go ahead and mark off factor it to get the actual zeros. So here we can factor a y, and this will leave us a negative y plus a 3, or if you will, negative y times y minus 3. Now, of course, this equals 0 if and only if y equals 0, or in this case, y equals what? 3. And so now when we think about this, of course, if y is equal to 0, x is 0, so we get 0, 0. And we'll just use this, and all of these are just obviously intercepts. And so now here we just get the intercept 0, 3. Just because it's a little bit more awkward because we're dealing with independent variable y. So let's go ahead and draw what we have. Now, another thing you can do or you can think about in this particular case is you don't really need to know what the vertex is because this opens obviously to the left because of the negative. But if you look at the intercepts here, you can just say midpoint will just be what? 0 plus 3 divided by 2, or 3/2. So that'll give you the coordinate of the vertex, where in this case we have the y value, and then we can say, all right, so x will be, we'll just use this one if you like, negative 3/2 times 3/2 minus 3. So we have negative 3/2, and of course this is just a negative 3. So if you look at this, this is just a negative 6 over 2. So that gives us negative 3 over 2 also, which is just what? 9 over what? 4. So we can draw in the actual vertex. So we have a 3/2 here. Not that it's important, but you know, you want your picture to look nice. And so in this case, so 9/4. So let's just say here, let me write this way. So there's a 2 and then there's a 3. And then here we'll mark this off. 1, 2, 3. So here's the 3/2. And then of course here the 2 and 1/4, say about right here. So if you just kind of really want to know where the vertex is, let me make sure it's a little bit more convincing. We'll just draw this in. This is just a little extra, little pre-cal. So we have the point in this case, what? 9 over 4, 3/2. And so now when we draw it, not that you have to know this, we've got this intercept and this intercept. So a nice symmetric curve here. And we want to rotate, in this case, about the y-axis. So now when you look at this, you've got some nice symmetry, but we've got a lower limit of 0, so don't worry about it. So y lives between 0 and 3. So we can pick a y and draw our rectangle. So this is truly the disk method because the region abuts the axis of revolution. So now we see r is just the value of the function. So when we input y, we actually get this function output. So we can just write it that way. So it's easier to integrate negative y squared plus 3y. And so now, again, we're good to go. We have the radius function, We know the formula, we have the interval of integration, and we're good to go. So in this particular case, by definition, we have volume will be pi, now 0 to 3. So let me mark this off. Sorry about that, 0 to 3, so you can see that. And so we have our radius function, which we square. So we have negative y squared plus 3y squared dy. So in this case, we have pi 0 to 3. So let's just square the binomial. So squaring the y, negative y squared gives us y to the 4th. Now we take the product, that'll be a negative 3y squared times the 2. So negative 6y, cubed. So again, the product is negative 3y cubed times 2 gives us a negative 6y cubed. And then, of course, we square this term, that gives us 9y squared. So the thing is, you might say, well, Professor Ron, you sure did do a lot of work here and all that. I mean, you can minimize the work and you don't really need to know the vertex, but sometimes it's nice just to give yourself a little bit of confidence that your graph is correct and that it looks correct or whatever. So again, that's an optional part. So now we can add 1 divided by the new power. So we have great lower limit, right? Y to the 5th over 5. And then we have 6 divided by 4, y to the 4th, add 1 divided by the new power, and then plus 9 over 3, y cubed, 0 to 3. And of course, with these formulas, don't forget your pi's. The pi's always just kind of drift away from us. So now when you look at this, we have 1/5 y to the 5th. And of course here, this will just give us a 3/2, 6 over 4 with a negative, y to the 4th. And then of course, 9 over 3 is just a 3, y cubed, 0 to 3. So now we can go ahead and finish the computation. So we have pi, substitute the 3. So we have 1/5 times 3 to the 5th minus 3/2 times 3 to the 4th here, and then plus 3 times 3 to the 3rd. And then, of course, I'll just go ahead and do this. Everything else, if we substitute the 0, these are all annihilated. So we just get that nice 0 there if you want to put that in. So now we can do some factoring because we like to factor. So note we've got a 3 to the 4th in every one of these. So let's get rid of that. That'll, we can deal with this. Okay, so this will leave behind 1 copy of 3 and a 5 downstairs, so 3/5. Here, we've got rid of the 3 to the 4th, so we've got the minus 3/2. And then, of course, we removed all of that, so we just have plus a 1. So this gives us pi 3 to the 4th. And we can just do a common denominator if you want, or we can just say, well, negative 1/2 plus 1, that's just what negative 3/2 plus 1 is negative 1/2. So we have 3/5 minus 1/2. Then just do a common denominator. So pi times 3 to the 4th. And of course, we need a 10 here. So this will be what, 2 times the 3 is a 6. And here we need the 2 into the 10 will be 5. So we have minus a 5. Now, of course, this, I kept that factored, but I knew nothing, well, nothing's going to absorb. So this gives us 81 pi. And of course, this is 1/10. So we get 81 pi over 10. So again, with your written up work, do the steps, do the computations. I want to see the work. Okay, that is one thing I will request of you. And if I don't see the work, I can't credit you for giving me a correct answer. Again, this is how I teach you. And I think of all of my students who finish their degrees at the university, and they're like, you bring your pencil and your piece of paper to the class. Maybe when you're doing your homework, you can use other resources, but you have to know how to compute. And I want to see that. I mean, so I want to see your computations and I want to see you work the problem. Doesn't have to be beautiful. I mean, my work's not beautiful. I mean, you can read it, so I want to be able to read what you write. So write clearly enough so I can read it. Okay, so now I want to do a washer method, and this is going to be an example from your WebAssign because it's a really good example. And several of you asked me about it. So I thought, well, I'll share this with everybody, so I'll just go ahead and share it with the class. This will be an example you work for your homework. And I thought this was a neat problem because it seems to be something that's coming up over and over. You notice sometimes you'll have a problem that says use the shell method, and you're thinking, dang, I need to use the disk method. This is too hard. Well, you're just trying to get some practice using the shell method. And of course, it doesn't matter which method you use, you'll still get the same answer. But this was a good example of the washer method. So here's what we had. This was the example. So I'll just say compute, excuse me, compute volume of the solid of revolution. And in this case, we had the following setup. We had the function y equals 6 over x squared. So we're going, and I'll just say this is the region. Region is bounded here, the region. So we have y equals 6 over x squared. We have x equals 1, x equals 3, and y equals 0. That's the region. And then we are to revolve about the line y equals 6. So this was a nice example, and it came up several times in your WebAssign questions. But it's not, the last problem was hard to graph, right? Quadratics take more time. This is an easy function, and it actually touches the horizontal line. I thought it was an interesting problem. So again, when you're given functions, let the functions guide you as to points. And so we want to make sure that we don't have to do excessive numbers of integrals, minimize that. So now what we can see, in this case, we've got y equals 0. And then we have, I'll spread this out, we've got 1. And then we have 3 here. So when we substitute 1 here, of course, we just get 6. So that's going to be a point that touches y equals 6. So we have this. And then, of course, when x is equal to 3, we're going to get 6 over 9. That's just 2/3, but it doesn't really matter. So we'll just say we're about right here. Of course, it's less, right? And so we've got this horizontal line here, y equals 6. And then, if you will, you can just go ahead and draw, just like you're drawing the 1 over x squared, just kind of fake it here and then just kind of fill it in. I like that. And of course, it'd keep going, right? And so now we can just fill in our vertical lines here and here. And then of course the y equals 0. So we get a nice region right here. So this is really easy. But the problem and the issue is that I don't know how to do this. Do I use the shell method? Do I use the washer method? And that's why I like the question, because it wasn't really clear. You're thinking we need to rotate here. And so you're thinking in this particular case, we can just use the variables that were given and then have the rectangle that's perpendicular to the axis of revolution and use the inner radius and outer radius. So in this case, the washer method would cut down on the amount of work. Otherwise, you're doing the problem like you did in WebAssign with the shell. You got this piece and that piece. I know you all work through it because I got questions about that too. So for instance, if we have an X here, so X lives between 1 and 3. So we've got that blasted non-zero lower limit. So sorry about that. And so we do our rectangle. And so now the beauty of this is that the outer radius is fixed. Ours will always be 6. And then the inner, again, this will just be 6 minus the function value. So R, in this case, will just be 6 minus 6 over x squared. So this is an excellent example. But again, with the washer method, you only have one integral. In an academic exercise, it's good to practice a technique. But when you're on a test, you know, your choice should be, if you have the flexibility, to go for the more efficient method. So now we've got everything we need. This implies the volume. This is just modified what? Modified disk. So this will be pi integral 1 to 3. Move this over. It's still nice and focused. Very good. So we have outer radius, which is 6 squared, minus inner radius, which is 6 minus 6 over x squared, quantity squared, dx. So again, the washer method is just 2 applications of the disk method. So you're thinking, well, I'm doing more work here, but yeah, it's still one integral though. I mean, at least using linearity, we kid ourselves that it's less work. So now I thought this was nice with the algebra here. You got a 6 squared and everything. So you can go ahead and just get rid of the 6 squared here and be done with that. So equals, of course. So we have equals pi times 6 squared. And that'll just, well, joy, right? 1. And then we have minus, again, we factored the 6. We have 1 minus 1 over x squared, quantity squared. So when you look at a problem like this, you want to think, okay, now I can clean this up and have a very straightforward add 1 divided by the new power. So we're fine with that. So this will give us pi times 6 squared. So we have 1 to 3. And now we've got 1. And now we want to expand this. So we square 1. Now we multiply this and hit it with a 2. So minus 2 over x squared. And then square this term. This will just be 1 plus 1 over x to the 4th dx. So square the binomial. Again, the product times 2, square, and a square. Now we want to distribute. So this will be pi times 6 squared, integral 1 to 3. So now we have 1 minus 1, minus minus, plus 2. I'll go write this as 2x to the negative 2. And then we have minus then we have minus x to the negative 4 dx. So again, distribute the negative sign and then just write these this way, since that's going to help us to do the antiderivative. So now we have pi times 6 squared, 1 to 3. The 1's absorb, and we have 2x to the negative 2, and then we have minus x to the negative 4 dx. So again, there's a little bit more algebra involved, but it's very straightforward, just like when we do arc length. You know, we're just kind of stuck with it, and we grin and bear it. So it's all right. So 6 squared. So now add 1, divide by the new power. So the new power is negative 1. So this is 2x to the negative 1 divided by negative 1. Good old power rule. Calculus would be a lot harder if we didn't have the good old power rule. And then now we add 1 divided by the new power. So we get x to the negative 3 divided by negative 3. So 1 to 3. So let's clean this up. So we have pi times 6 squared. And now, if you will, this will just be 2 over x with a negative. So negative 2 over x. Just making that, now we make it user-friendly. We get rid of the negative so it's easier to evaluate. And then, of course, here the negatives absorb, and we get plus 1 over 3x cubed. So when you look at examples like this kind of reminds you of what we've been doing forever. So that at least makes this part of the test pretty straightforward. Now, let's go ahead and evaluate. So we have pi times 6 squared. We want to use the fundamental theorem. So we're going to substitute 3. So we get negative 2 over 3 plus, and now we get 1, and we have 3 times 3 cubed. Minus, now we substitute 1, not difficult though. So we get negative 2 over 1. That's just negative 2. And then, of course, here with the 1, we just get plus a 1/3. So that's not so bad. So this gives us pi times 6 squared. So we have a negative 2/3. And here we've got a plus a 1 over 3 to the 4th. And now we have minus minus. So we have plus a 2 and then minus a 1/3. And I'll finish this. I don't want to crowd the bottom of the sheet there, so I'll just go ahead and use a new sheet here. So now notice we've got the negative 2/3 and the negative 1/3. That's just a negative 1. So we get pi times 6 squared. So if we add these, we've got 1 over 3 to the 4th. We have plus 2 minus 1. So the minus 1 here. And then, of course, the 2 minus the 1 is 1. So pi times 6 squared. And so we have 1. Now we can just write our 81 plus a 1. So now we get a common denominator. And then, of course, we'll be able to retire some of these 3's here. So we'll just go ahead. Well, I'll go ahead and do it this way. Then once we move past this last step, we can factor. So 81. So this will be 1 plus 81. And so now we have pi, and if you will, 2 times 3, 2 times 3. And then, of course, the 81, we just have a 3 times a 3 times a 9. That is, 81 is just 9 times 9. So that's going to retire the copies of 3. And then, of course, we just have what, an 82. So the 3's absorb. So we get what, a 2 and a 2. So we get pi times a 4. The 9 hangs out. And then, of course, the 82. So the 82 times 4 is 320. Plus 8 will give us what? 328, right? So we got 328 pi over 9. So when you look again, at this kind of example, unless I specify the type of technique you want to use or whatever, you have that control. And you can set up the problem however you like with whatever mechanism that works for you. So like I say, I thought this was a good example because it came up several times in questions. And so the washer method we see is a good technique for this one. Now, there was an example from your WebAssign that I just wanted to mention. This was with the arc length. I had several questions about this. And let's see here, will this be, okay. Well, let me first, I'll mention this kind of in passing as a summary. Let me go ahead and do an arc length that is kind of more like I'll do on the test. This is the asteroid problem from 7.4, and several asked about that, but I'll do that in the summary. Let's do an arc length that's a little bit more relevant to the test. So here we want to compute length of curve. So length of curve is just arc length. So in this case, we have, oh, and this is a nice problem. It gives us the values of x. So x will live between 1 and 27. And the curve is y equals 9 minus x to the 2/3 raised to the 3/2 power. Again, I was talking with one of your classmates, and we talked about how these functions are a little bit strange looking, so that we end up with integrals that you can do. As we learn more techniques, we'll be able to do maybe some simpler functions that don't give us the nice user-friendly integrand. So, but we have to work up to that. So in this case, we apply the definition. So remember, arc length is just a to b, and we'll do the principal square root of 1 plus y prime squared square root. So let's go ahead and do the due diligence, so to speak. So we have y prime will be the derivative of this function. Again, the inner function is 9 minus x to the 2/3. The outer function is the 3/2 function. So we get 3/2 9 minus x to the 2/3, again, subtract 1 to the 1/2, times the derivative of the inner function. Of course, we get a 0 here. So by the power rule, we get a negative 2/3 x to the negative 1/3, okay? So now let's clean this up, bring all the numbers together. So we have 3/2 times a negative 2/3, 9 minus x to the 2/3 raised to the 1/2 power. And then of course here we have 1 over x to the 1/3, just to bring that downstairs. So now the numbers here absorb, leaving behind the negative. So we have negative 9 minus x to the 2/3 to the 1/2 divided by x to the 1/3. So that's y prime. And again, this is important because with the asteroid, we don't want to have integrands that blow up. We have to have the y prime to be C1. So this is good here. This makes sense. We don't get the division by 0. So this is a good interval. Again, we have a C1 function. So now we want to square this out and add it to 1. So we need the integrand. So 1 plus y prime squared will be 1. So we square this, and now let me just write it out. So we have negative 9 minus x to the 2/3 to the 1/2 x to the 1/3. We get to use our law of exponents. So this gives us 1 plus. So when we square this out, the negative absorbs. And of course, the 1/2 times the 2 leaves us with a 9 minus x to the 2/3. And then, of course, squaring downstairs gives us x to the 2/3. So now we want a common denominator. So we have x to the 2/3. So of course we need to multiply here by x to the 2/3 plus 9 minus x to the 2/3. So of course these terms absorb, and we're left with 9 divided by x to the 2/3. But of course, hallelujah, we have a perfect square. We get 3 over x to the 1/3 quantity squared. So the idea is that these functions look a little bit strange, so we actually get integrals that you can do. Of course, with the surface area, you got that extra factor there that kind of helps you out with the integrals. So now we can use this formula. So this implies that S is now the integral from what, 1 to 27 of the principal square root of 1 plus y prime squared. So we have the square root of 3 over x to the 1/3 squared dx. So this gives us 1 to 27. Of course, the square root of the square is the absolute value. And we can just go ahead and write this as 3x to the negative 1/3 dx. But of course, this function on this interval is positive. So we can actually integrate this without the absolute value. So this will give us 1 to 27, 3x to the negative 1/3 dx. So now this is a doable integral, kind of like the asteroid's the same thing. You get a nice doable integral. So now when we look at this, we're thinking, okay, we'll use linearity. So this will be 3 integral 1 to 27 x to the negative 1/3 dx. And so now we'll just add 1, divide by the new power. So we have 3. The new power here will be 2/3. So we reciprocate the 2/3 and get 3/2. So x to the 2/3. Division by 2/3 is multiplication by 3/2. And we evaluate from 1 to 27. So now, of course, we just have a 9 over 2, which we'll just remove to the left to get it out of the way. And so we have 27. We replace x with 27 to the 2/3, and then minus 1 to the 2/3. So this gives us 9/2. And now, of course, we can take the cube root of 27, which is 3. So this will be 3 squared. And of course, the 1 to any non-zero power is just 1. So that's minus 1. Very easy. So we get 9 over 2. And of course, this is 9 minus 1, which is 8. So the 2 absorbs into the 8. So we have 9 times 4, which is 36. Now, the thing is, sometimes with these interesting functions like this, you get answers that kind of surprise you. It's like, oh, there's no radical, there's no 13 or pi or square root of 17 or something. These can be really surprising based on what we normally get. So don't be surprised where you have an unusual looking function and you actually get a nice arc length. Well, the thing is, you can see in general, arc length is Pythagorean, and it requires a lot of algebra. Okay, let's look at, where's one I wanted to do. There's an example that I want to do with, where is that example? Let me find it over here. We've got the arc length. There's another arc length I want to do. Let me do a shell method. Let's do a shell method. And then I'll go over that arc length. So here we go. So in this case, we want the volume of the solid of revolution. So example, let's see here. Yeah, this will work. Compute volume of the solid of revolution. And in this case, we've got the following region. Oh, here's a good one. So it says the region in the first quadrant bounded above by the following line. So region is 3x plus y equals 6, something linear for a change. And we've got, let's see, the x-axis, so we have y equals 0. And then on the left, let's see, okay, and then on the left by the y-axis, so we have x equals 0. So that's the region. And then we want to, in this case, revolve about the line, revolve about line, x equal -2. So again, we have a region, linear, a linear function. We have the x-axis and the y-axis. That will give us a region, and we want to revolve this region about the line x equal -2 to compute the volume of solid of revolution. And just for practice, let's just use shell. You know, if you actually computed something with a different method that I didn't say on the test, I probably wouldn't care. If you did it correctly, I mean, I can't really quibble about that. So yeah. So now when we look at this, we're like, okay, well, if we look at where the boundaries are, we just want to find x and y intercepts. So let's go ahead and do that. So now here, we can look at this. We'll just say, okay, well, when x equals 0, we have y equals 6. So this gives us 0, 6. Don't you like the nice numbers? When y equals 0, we have 3x equals 6, if and only if x equals 2. So this gives us 2, 0. So we'll spread this out a little bit. So we've got here, we'll just mark this off as a 6. And so we've got like a 3 here and a 0. And then we'll spread this out a little bit, a 1 and a 2. So just a little bit liberal with the x-intercept. So here's 1 and here's 2. So again, we've got this triangular area. So we've got the curve 3x plus y equals 6. And so we get this. Again, bounded by the y-axis, x equals 0, and the x-axis, y equals 0. And now we can mark in x equal -2. So we have x equals -2. And that's where we want to revolve. So again, when we look at this, you know, shell method is fine. And in this case, remember with the shell method, we've already got the intervals here of integration, which is even nicer, 0 to 2. And then we've got our rectangle parallel to the axis of revolution. So we've got x living between 0 and 2. So we just pick an x here and then draw in our rectangle. The visual part of these applications is really nice. I mean, let's face it, it does make the problem pretty simple. So now, in this case, h will just be a function of x. So we just solve for y here. So this just says if and only if y equals 6 minus 3x. So we have 6 minus 3x for the height of the strip. And then, of course, now we can just do the difference here for the distance to the axis of revolution. So this will be P equals x minus a negative 2. So this will just be x plus 2. So again, the shell method here is really easy to set up. Just think about shell method. You don't have the squares, so you don't. Sometimes you have difficulty. I mean, let's face it, but squaring, usually the powers are smaller, so maybe that can be one vote of confidence for shell method when you use it. So now we're good to go. So this implies that the volume, and let's see here, shell method. Okay, so volume, just making sure I'm following the directions of an old test. So we have volume equals 2 pi. Remember, with the shell method, we have the factor of 2 pi from the difference between the cylindrical shells that we showed when we derived that formula. So we have what, in this case, 0 to 2. And now we have the distance to the axis of revolution, which is x plus 2. And we have the height of the strip, which is 6 minus 3x dx. So let's clean this up a little bit so we can integrate it. So we have 0 to 2. So now let's just distributive law. So we'll have 6 times x, 6x, and then x times a negative 3x. So that's a negative 3x squared. And then 2 times a 6 is a 12. And then, of course, 2 times a negative 3x is a negative 6x. Well, very nice. Those will absorb. So we get 2 pi, 0 to 2. And, of course, these two absorb. And we're left with negative 3x squared plus 12 dx. So, of course, we're lazy. We got 3 and everything, so let's get rid of it. So we've got 2 pi times 3, 0 to 2, and that'll leave us with a negative x squared, and then, of course, plus a 4. So just make the number smaller. It's not required, but it's just an extra packaging in the way that we can move. So now we've got 6 pi. And so we have, and of course, we can go ahead and add 1 divided by the new power. So this will give us a negative x cubed over 3. And then, of course, an antiderivative of 4 relative to x is just plus a 4x. Evaluate from 0 to 2. So this integral is a little bit less complicated than the others. We had more work to do here, but it wasn't really difficult. So now we have 6 pi. Now, of course, the lower limit annihilates both of these. So this will give us a negative 2 to the third power divided by 3 plus 4 times 2. And then, of course, we get the 0 terms, which I'll just put as a 0 there to remind you of that. So we get 6 pi. And now we have a negative 8 thirds, negative 8 thirds plus an 8. So we'll go ahead and factor the 8. So we have 6 pi times 8. So this gives us a negative 1/3 plus 1. So of course, negative 1/3 plus 1 is 2/3. We can do that in our head. So we got 6 pi times 8 times a 2/3. But now, of course, we can factor this. So this is a 2 times a 3 over 3 times 8 times a pi. Of course, the 3's absorb. So we've got the 2, we've got the 3, and let's see here. And my 2 pi, we got that. And let's see here. Let me just make sure we got everything. 2, and we've got another 2 here. Number 2. right there. This 3 I move over here, but then we still got that other copy of 2. So I need a little room for that. Sorry, pi. So again, we've got the 2 here, we have the 8, and then we have the 2 times 3. These absorb, but I left out my 2 there. And so now we get a 2 times a 2. So that's a 4 times an 8 times a pi, which gives us 32 pi. There's no part of the problem that's unimportant. And again, this is why I factor everything and why you write everything out. So if something looks a little odd, it's like, wait a minute, was I a good court reporter? Unfortunately, in calculus, we remind ourselves, if you've ever seen a court reporter, they take down everything that is spoken. They describe the dialogue, everything that happens in the courtroom, and they're like just going. And I remember when I was a little kid, my aunt did some of this as the register of deeds for the county. And she had to learn to do that with a shorthand machine, which I don't know if they even use anymore, but I would have to dictate to her while she would type, and then she would read it back to me. And I thought that was amazing. And that's why I keep saying we're like court reporters. We kind of write down and write down and write down, and then occasionally we slip and say, wait a minute, I dropped something somewhere. And so that's why I always say we have to be court reporters when we do calculus. So now what we're seeing here is that we make a figure that seems relatively pleasing geometrically, but using the shell method, it's very attainable. So we get a volume of the solid of revolution 32 pi. So this is a very neat problem. And the shell method, all these methods, even though they're definitions, they certainly have their merit, and you can be very creative if you want. Now, there was an example that I wanted to do from your homework to go over it. Let's see here. Where is that? It's the asteroid. And I'm gonna summarize it, but I want to do another example, like just a little surface area example that I didn't get to in your homework. Let's see, this is, yeah. Because I think I did 1 or 2, but let me just make sure. Let me find it. So, okay, we did that one. And if not, I'll just find one. Okay, now you're gonna have to help me out with this if I may have done this one, I'm not sure. Because I don't know if I have one on this test that has a solid, area. So let's see here. Yeah, let me do this one. And I'll run over here to your WebAssign and draw one of those. Oh, of course, they always say bad request when I don't stay engaged with the WebAssign long enough. So they're trying to keep other people out. Okay, so let's see here. Let me go here. ArcLink, there we go. Okay, let's see here. Okay, and let's see what we have here. So we've got this one, and oh, here's a good one. Okay. So let me write this one down. So we've got, and I'll share this with you. Revolve the curve about the x-axis and then compute the area. Okay, so in this case, yeah, so we have y equals 1/3 x cubed. And in this particular case, we have x living between 0 and 3. And compute area of surface. This is kind of like the last one. So I want to do one to make sure we've covered all the aspects here. So in this case, so let me share this. So in this particular problem, what we want to do is look at this as a curve like we did the arc length problem. And in this case, WebAssign says revolve about the x-axis. So revolve let me get that V. Revolve about x-axis. So in this case, we'll go ahead and just get a picture. This is a nice college algebra function. Now it's a little more squatty because of the 1/3, but I'll just draw it out nice so we can see it. So of course here with the 3, we'll get 27/3, which is 9. So we'll just kind of say we've got a 9 there and a 3 here. Kind of use that as a focal point and do the symmetry over here. So we'll say curve starts here, nice horizontal tangent, and then up to here. So we'll stop there. So here's our curve. And what we want to do is revolve about the x-axis. So now what's nice about this, we've got a nice setup region that is x lives between 0 and 3. And then we can pick an x. And in this, well, when we don't need the, sorry, creature of habit, we don't need the rectangle here because we're not getting a solid of revolution. So we have our little piece here, our delta S. And so what we want in this case, we have our element of arc length, which we have to compute, and then we need the distance to the axis of revolution. In this case, this will just be R equals 1/3 x cubed. So that's easy to do, but we need our element of arc length. So now in this case, let's go ahead and look at y prime. So y prime will be the derivative of 1/3 x cubed here. So this will give us 1/3 times a 3, subtract 1, we get a 2. The 3 and 1/3 absorb and we get x squared. So now this implies that 1 plus y prime squared will give us 1 plus x squared squared, which is 1 plus x to the 4th. So we see that these integrals can get really, really complicated fast without the additional distance to the axis of revolution. That's why the area of the surface is usually a simpler calculation. So now area will just be 2 pi. Well, of course, let me complete this. I don't want to run to the problem and not go ahead and write everything down. So this implies equivalently, in this case, we'll have the ds will be the square root of 1 plus x to the 4th dx. And then, of course, if you want the delta s as I've written there, you can write it this way in terms of the partition, if you like. That way I'm not skipping this important step. So now this implies area of the surface. Again, when we make this surface, this is going to be a nice, beautiful surface, like a French horn, so to speak, when we make this. So as engineers, future engineers, you or architects, you can be very creative in the buildings you design. So now this gives us, in this case, a 2 pi integral 0 to 3. And now we have our distance to the axis of revolution, which is 1/3 x cubed. And then we have our element of arc length, which is 1 plus x to the 4th 1/2 dx. So this is a doable calculus 1 integral, thank goodness. So now we can see that u equals 1 plus x to the 4th. And so du is 4x cubed dx. So when we look at this, we just need an additional copy of 4, and then we can, of course, pay for it. So now we'll go ahead and bring out the 1/3. I could bring in the 2, but just forget about it. Make it easy. 2 pi over 3, leave a little space there. And then 0 to 3. And then 1 plus x to the 4th 1/2. And now we can fill in the 4x cubed dx. And then it's table ready if we pay for the 4 here. So now this is a table ready integral, ready to go. Add 1, divide by the new power. So now, if you will, the 2 will absorb into the 4 to give us a 2. So we have pi divided by 2 times 3. And so add 1 gives us 3/2. Reciprocate gives us 2/3. 1 plus x to the 4th 3/2 power. 0 to 3. So what's neat about this is that, like I said before, we actually get an integral that we can do. And again, divide, add 1, divide by the new power. And so we can factor this. So this gives us 2 pi and bring the 3. So that gives us a 2 times a 3 times a 3. So just put all the 2's and 3's together. So we have 2 times 3 times 3, and now we have a 2 pi. So now we want to substitute. So in this case, we substitute the 3. So that's 1 plus 3 to the 4th power 3/2 minus 1 plus 0 to the 4th, still 0, but not 0, right? 3/2. So the 2's absorb, and we're left with a pi over 9. And then we have here, we've got an 82, right? This is an 81 plus 1. So this is 82 to the 3/2. But notice 82 is just 2 times 41. So there's nothing beautiful in that to factor. So we're kind of stuck with it. And then, of course, we have minus a 1 to the 3/2. So this gives us pi over 9. So we have 82 to the 3/2, or we can write it this way if you like, 82 times square root of 82 minus 1. So what I wanted to do today was just kind of give you a review of the types of techniques. So like I said before, normally I don't do this. I thought, well, you all can study on your own, you're fine, you don't need me. But I thought, just as something different that I thought I could add. Again, use this as you need, but just remember, on the test, I will evaluate you on the standard techniques. They're not going to be any formal proofs. For instance, it says like prove that the formula of the square pyramid. I will say make sure you look at the cross section. That's one thing I didn't do today. I'll let you review that. I have to have something challenging on the test, right? So make sure that you look at the cross section. We covered that. But that's a very simple technique. You just find the area of the cross section and integrate it. So that will be a very simple thing. But again, when you prepare, do as many problems as you can just to get yourself honed for the type of executions that you have to do on the test. No formal proofs. And also, like I say, I'll send out another email and announcement to kind of remind you when things will be available and to remind you of the things you need to do. Now, the one thing I wanted to mention, and I'm just going to summarize this, this was the arc length problem from the asteroid. And several of you asked about it. Forgive me just to summarize, but this will help you. This was, we did the roof area, but the asteroid is not a hard problem, except they give you, WebAssign gives you a picture of it, and you see that on the axes, you've got these points. And that should clue you into the fact that, well, the function's not differentiable there. I can't just mow over that. So what I wanted to note here, the integral we get is simple, but it's kind of like the problems we've done with arc length. We have an asteroid curve, which we're actually going to parameterize later in chapter 10, but we see it's symmetric in X and Y. And so this graph would have to be symmetric relative to the line y equal x, which you can see from the picture they give you on WebAssign. So you can actually find the value of x where the function or the curve crosses the line y equal x. So you get 2 root 2, comma 2 root 2, and then you get negative root 2, comma negative root 2. So in the first quadrant and the third quadrant. Now, the issue here is with these points, we need to avoid those. So what we can do is we can just look at the upper curve here. When you actually solve for y, you get an upper curve and a lower curve. And then, of course, you can compute the domains here. They give you that on WebAssign, but this is all just college algebra. But the idea is when you look at y prime, what you can see here is we have division by 0 at 0. So we couldn't integrate from 0 to 2 root 2. That would blow up. So with the nature of the derivative here, we can just go ahead and use the fact that the curve basically has 8 pieces that are all symmetric and integrate from 2 root 2 to 8. And then multiply the result by 8. So that's the hard part about the problem. The easy part is really easy. So when you compute the derivative and then you do 1 plus y prime squared, this is like the problem I did for the review. Remember, we got something that looked exactly like that. It's the same thing. 2 over x to the 1/3 quantity squared. So this part's just like we've been doing. And then when you actually do the computation, it's a very simple add 1, divide by the new power. But remember, in this case, you've got to multiply the result by 8 because you're chopping it up into 8 pieces. And so you get 48. I think in the other problem, we got 36 or something. But again, as you're looking at this problem, just remember the only analysis is just involving replacing y with x and finding where the curve actually crosses the line y equal x. And a lot of you work very hard on this problem, and I have great respect for you. It was interesting. One student worked through all of this and then just made a simple error in this part and thought, oh, I just must have messed up this problem when they had actually done a really nice job. So there are times, when you look at the curve and there are places where it's not C1 and you can't just mow over it. Okay, so that's a thing that we're going to talk about when we talk about improper integrals. We can't integrate things that are infinitely discontinuous in the interval of integration. So if we do it, and of course the limit doesn't exist, then that's not a very good way of doing it. So I just wanted to review that because several of you have asked about it. So I will have one conference hour today. And then, of course, tomorrow is the college community day, but I'm going to have my office hours. I'm going to have my conference hours. I'll just do college community in between because I'm going to be available. And I have 3 sessions on Thursday. So if you have additional questions and you just want to think you would rather test on Friday, and if you have additional questions, go ahead and send them. I will be available. My students come first. So you will have access to me while I'm doing College Community Day because that's the way I want it. So again, as you do your work and you do your quizzes and you work through your homework, focus on the fundamental constructs of doing the examples, of working the algebra, working the arithmetic, because that's really all we're doing. The only fancy part is, I guess, the inverse trig functions that actually have that unit circle, which, can get rusty at times. But like I say, I will have another email out with information about the test, and I'll send out email invitations for my conference hours. And of course, you can continue to send WebAssign messages, and I will do my best to help you, to assist you. But again, enjoy this nice weather because it's not going to last. It's supposed to get cold. I doubt we'll get any snow, but it's going to get cold. But I appreciate your attendance today, and I wish you well as you continue to prepare for your exam. I know you're working hard, so I look forward to some really good test papers. So everybody have a great day, and take care of yourself. If you venture outside, please be careful. And if I can help you, just let me know. Bye, everyone.